So, like many of you before, my topic is also generative modeling, and also similar to prior talks in this workshop, I am interested in the target measure for which we want to do generative modeling having some low dimensional structure. Specifically, we are interested again like as introduced by Wenjing and then Seating and Luke this morning, we are interested in target measures which are singular but have absolutely continuous low dimensional structure. So, they are absolutely continuous on some lower dimensional manifold, which seems to be a very common assumption in data science. Again, this is also from the same paper that Wenjing mentioned. Here I am showing you fixing the latent dimension of the generative model. I believe there was a GAN that was used here. This is the latent dimension. If you make the latent dimension unrealistically high, you get images that do not really look meaningful, and if it is too low, then you get some artifacts like this weird looking tail. So, we believe that the latent dimension is still not as high, not nearly as high as the number of pixels in the image, but something intermediate, and it has been discovered empirically, and we believe that this is true beyond image generation. Now, in scientific applications, which is closer to the things I care about, physical measures or measures that are naturally associated say with dynamical systems also have a low dimensional structure. Here to illustrate that, I am showing you a 2-dimensional distribution associated with a 2-dimensional chaotic dynamical system, and this is the physical distribution, which is like an invariant, a special invariant distribution associated with this dynamical system. And you can see that this measure kind of looks strange, right? It is not absolutely continuous in 2D, but in this direction, like parallel vertical direction, it does not even look continuous, not absolutely continuous, whereas along these filaments it looks very smooth. So, in some directions you have a density, in others you do not have a density. And like many of us in this workshop, I am interested in doing something with these samples, right. So, suppose you are sampling from this distribution with a low dimensional structure, what do you do with these samples? Hopefully, we can use these samples to solve inverse problems, for data assimilation, for other downstream computational tasks. And the argument is basically that if the distribution that we care about, let us say associated with a dynamical system, has a low dimensional structure, this low dimensional structure carries over also to the target distributions for these other computational tasks. So, as an illustration, suppose you have some very high dimensional climate model that is producing some hidden orbit, and you care about, and you have some observations, and your target distribution is sampling from the state variable of this high dimensional dynamical system given observations, then this is actually a Bayesian inference problem. This is a posterior distribution in data assimilation, and this distribution also has a low dimensional structure because we believe this dynamical system naturally has a distribution with an absolutely continuous low dimensional structure. Okay. This is all to say that this talk will be about asking questions about when we can sample from target distributions with a low dimensional structure. Two specific questions. One is when you take a generic generative model, let us say a score based diffusion model, and there will inevitably be errors in whatever, in how we learn or approximate the distribution. Can we ask when is the support of the generative model robust to these learning errors? The reason we are asking this question is that we believe, okay, there is some low dimensional support of the true target distribution. So, each sample from this support is a plausible sample, it is physically meaningful. So, even if we do not get the distribution right, as long as we sample from the support, maybe this is a guarantee that we would like in in scientific applications. The second question, a theoretical question also motivated by scientific machine learning applications, generative modeling for science, is if we learn one step of a dynamical system, can we approximate the natural invariant measure associated with this dynamical system. So, this learned dynamical system itself is a generative model, and it is only learned with some short term data. So, then when can we get guarantees? Specifically, I am looking at chaotic dynamical systems. When can we get guarantees that we sample from the invariant measure associated with this dynamical system? So, I hope these questions are clear. So, the first part of this talk will be about analyzing generative models to understand when we can get guarantees that they will sample from the support of the target distribution, even under errors. And also feel free to interrupt me at any time if you want a clarification. Yeah. So, let me try to explain this question about the robustness of the support that I mentioned, first with pictures. So, here is the target distribution. As you can see, the target distribution is supported on these two almost one dimensional curves, right, in two dimensional space, and then there is a specific density. This here the density is higher than here. Now, if you now take a score based this is a diffusion model that is producing, this is the kernel density estimate using samples produced by a diffusion model, but with errors. So, the underlying score of this diffusion model has now order 1 errors, which are just randomly added, okay. And now you can see you get this distribution. It is wrong as expected. However, it is wrong in an interesting way, in that you can still see, roughly speaking, the support of the target distribution that is contained even though there are errors in the diffusion model. So, how do we formalize this empirical observation? So, many people have asked this question, what does it mean to truly sample from the data manifold, which is supposed to be a loose term for the support of the target distribution from which the data are coming. And can we say, is this only going to hold for a specific diffusion? Is this a fluke basically? If I change the target distribution, will I still have this property? If I change the generative model itself, will I have this? If I use a flow based diffusion, a flow based generative model as opposed to a diffusion model, will I have this property? This is the question. Okay. So, to understand that, let us formally look at generative models exactly the way Seating described in her talk. We think of generative models as just an algorithm which takes some finite number of samples from the data target distribution, which will be written as p data, and it generates more samples. The thing to note is that I have written them in high dimension. So, capital D is this ambient dimension from which we are getting the data. Okay. So, no matter what kind of generative model you use, there is an underlying optimization problem that is solved, right. So, you are trying to learn some vector field, which will some true vector field Vt by solving some optimization problem, and this vector field is used to generate the samples. Like in a score based diffusion model like DDPM, DDIM, variants of all these different generative models, the vector field is equivalent to a score of a noising process, as we have seen before in previous talks. This noising process corresponds to initializing the process with some samples that we are given from the target distribution, maybe adding some noise, and these scores are the scores gradient of the log density associated with this process. Okay. And this is approximated with a neural network. Now, in a conditional flow matching, stochastic interpolance, or flow based generative models, this vector field is again represented as a neural network, but the principle is that the vector field has to be such that it flows some P0, which is some easy distribution. I will just use this instead, some easy distribution to the target distribution in finite time. In other words, we have some loss function. This is our optimization problem. Every different loss functions used in various different generative models are equivalent ways of probably representing this, where V theta is a neural network representation of some underlying vector field Vt, and we want to make them as close as possible while satisfying, say if it is a deterministic model, then satisfying a continuity equation. If it is a stochastic generative model, then satisfying some Fokker-Planck equation, which is such that at some finite time tau, you get samples from the target distribution. Yeah. So, this is just the basic setup of pretty much many different generative models. But of course, this was also in Seating's talk, and probably every talk on generative model, which every speaker I think is compelled by the cuteness of this dog to use the same pictures. So, but the only difference in this picture is that I've reversed the direction of time, okay, because the process I want to analyze is just the reverse process or the generating process of a diffusion model. So, initial distribution is the noise distribution, final distribution is the data distribution. So, in this way we can fix the direction of time to be this way, so that we also can think of flow based generative models and the reverse process of a diffusion model as the one we care about analyzing. Okay. And the question we are interested, the purpose of this analysis is to see for whatever loss function you have to represent this neural net that will be minimized to represent the neural network for the vector field, there will be some inevitable errors, right? How do these propagate along the dynamics of the generating process? Okay. And ultimately we want to understand this error propagation to answer the question of, because there are errors, the distribution that is generated is going to be different from the target, but is it going to be different from the target in a way that retains the support of the target distribution? Yeah. So, to answer these questions, let us formalize what are generative models and generative models as dynamical systems. Okay. So, the reverse process of a score based generative model, for instance, or any of these flow matching based generative models are just some Markov chains that will take you from some distribution which usually has a density, and that density will be rho 0, to the target distribution that may or may not have a density, but approximate density rho tau. The approximate density you can think of as, if you do not run your diffusion model all the way until the final time tau, but if you stop just prior to it, then you will still have a density. That is what rho tau is, or like you can think it's like a small convolution of the target density with small Gaussians. Okay. So, formally you can take the algorithm itself and think of it as a random dynamical system. Okay. What is a random dynamical system? It's just a dynamical system with randomness in it. Okay. So, this includes all the classes like stochastic dynamical system, non-autonomous stochastic dynamical systems. Together we will call these random dynamical systems. It is non-autonomous because at each time we apply a different function ft, and the w here represents just say the Wiener process. If you have a stochastic generating process, then there is some additional randomness, and that is what is represented by w. Okay. So, our generative model is a composition of these f's with the subscript t, which is what we apply, is the function we apply to the samples at time t. And then in the composition of t such maps is our generative model. Okay. So, what does this have to do with the vector field? Well, you can simply think of this as the time integration of the vector field that we learned. Okay. So, for instance, for a score based generative model with the score being this guy s at x at tau minus t, this is the disk time integrated version. So, you can just take Euler Maruyama, people do other fancy things, nobody does exactly this, right. But whatever, there is some discrete process, the time discrete process, continuous in space, discrete in time, that represents our generative model, and that is what this ft is. Okay. And f with the superscript just means it's an exponential notation that's very common in dynamical systems, just represents the composition of the f's with the subscript. Okay. Of course, corresponding to these dynamical systems, we have this dynamical system, we have a corresponding flow of the probability densities, right. So there is an operator which I will denote as LT. This is also time dependent because at each time the vector field is changing, and you can think of this as an integral of some conditional probability. So this is the conditional probability kernel, the density associated with the conditional probability or the transition probability, and this operator is LT that tells you how densities are flowing according to this generative model. Okay. So all we know is that rho at time 0 is the rho 0 corresponding to the easy distribution, and rho at time tau should be close to the target distribution if all is well with your generative model. Now writing this as a random dynamical system means that we can leverage a lot of random dynamical systems theory, which is a classical area, a subset of dynamical systems theory. And then there are concepts like Lyapunov exponents, which some of you may have heard of, which tells you how perturbations to orbits will behave. And so orbits here are orbits of this generative model, so how your samples propagate, okay, in path space. Okay. But if you haven't heard of these random dynamical systems theory, don't worry, because I'll tell you all that is needed in order to analyze our generative model. Okay. So in sample space, if we make an error to the generative model, so this is what we're interested in, because let's say Ft is the dynamical system at time t, which represents what happens at time t to our samples, right, under the true vector field Vt, okay, but we don't know the true vector field. So let's consider an additive perturbation of L infinity norm epsilon, say chi t is a unit vector field which represents the error in the dynamical system. Where does this error come from? It could be from anywhere. When you solve a regression problem for Vt, you represent Vt as V theta t, and so there is an error that is made, and that is what I am representing as an additive perturbation to the dynamics at time t. So I hope this is clear. It is the error that comes from a neural network approximation. Could be anything, could be approximation error, regression error, wherever the error comes from, that is what I am writing here as the chi t. So correspondingly, we have a perturbed generative model, which I will now denote as Ft epsilon. Okay. So when epsilon is 0, you have a true generative model that is going to produce samples from your target distribution, and if epsilon is non-zero, it is going to produce something else. Okay. So the perturbed dynamical system again has the same notation. You have f to the t, so exponential notation is just the composition. So this should be t minus 1, my bad. It is the composition of t steps. Okay. And you can also think that corresponding to this epsilon error that we make in the dynamics, we can look at these errors in tangent space when the epsilon is very small. So in the limit epsilon tends to 0, so infinitesimal errors are propagated along orbits of the generative model according to this equation. Okay, this is the tangent equation. If you haven't seen this before, it is exactly what is written here. It is how much at time t, if you start at some x, if you are at some x at time t, and you apply the perturbed dynamical system minus the original dynamical system, what is the difference? Okay. That is given if you do Taylor expansion of the Ft assuming smoothness. This is the Jacobian of Ft multiplied by this vector field. So this vector field ut tells you what is the direction in which errors are moving because you have made an error in the original dynamical system. I hope this is clear. Okay. Now this is all how errors propagate in path space or in sample space. Right. Correspondingly in probability space, there is an operator which is just the push forward of Ft, but Ft epsilon. With the error, the push forward itself is different. Right? So this means if we have densities, so rho t, where is this? Oh, here. Rho t epsilon are perturbed densities, rho t 0 are the original densities, corresponding to this perturbed operator LT epsilon, we have like a change of variables formula with the perturbed dynamical system. Okay. So this is our model for taking the generative model at each time and perturbing it to represent errors in optimization. Okay. U? Yeah, U is a vector field. Okay. So you can take U0 to be some arbitrary vector field. Okay. Let us say the 0 vector field. Then at time 1, what is the vector field which corresponds to the difference between the orbit of Ft and Ft epsilon? Yeah, it is the vector field corresponding to the perturbation of the dynamical system. So in the limit of infinitesimal as epsilon tends to 0, you have infinitesimal perturbation to the dynamics. This means that there is an infinitesimal error. So the error is in the tangent space, and that is what this ut is. So uts are errors in the tangent space which represent the errors in the dynamical system in the limit of infinitesimal, in the limit epsilon goes to 0. Okay, so we want to ask, okay, if you make all these errors, of course you do not get the data distribution, you get p data epsilon. Okay. Can we ask in the limit of infinitesimal errors, how close is p data epsilon to p data? Okay. So you can do a very simple calculation to get a result like this. Okay. So this just comes from integration by paths and is kind of fairly obvious. If you have a absolutely continuous measure, that means that p tau, which is supposed to be the target distribution, so at time tau, this is the density of the target. If you do have a density, then the change in the density with respect to epsilon. So you can think this is the same as saying p tau epsilon minus p tau 0, which is the true target density, is equal to epsilon times this guy. Okay. So how much is p tau epsilon different from p tau as epsilon tends to 0, or for small epsilon, is given by this expression on the right hand side, which of course depends on the error chi and this score of the densities St. So you can really think of this sum as some scalar field, but the important thing to notice is that this scalar field is multiplied by the true target density. So this is saying that wherever there is error, the errors are supported where the target is supported. Okay. So you can derive this in the limit of infinitesimal errors. This is just to say that if you take for any generative model that has some mild regularity property such that all this integration by paths can go through, you have this property that in the limit of infinitesimal errors, the errors in the generated density will be supported exactly where the target is supported. So the support is retained for infinitesimal errors. Okay. The more interesting question is what happens when you do not have a density. If rho tau does not have a density, these operations are not legal, then how can we quantify the errors that you will get in the generated density? Okay. So before I tell you about that, let us again look at this diffusion model. I am so sorry that you cannot see all these pictures, but these are CIFAR 10 images on the left, and on the right are CIFAR 10 images generated by a diffusion model that is pre-trained on CIFAR 10 images. But now in the generating process, I have added order 1 errors. Okay. So these are not even infinitesimal errors, they are like pretty large errors added to the score of the reverse process. Now these images look pretty much like indistinguishable, and you can calculate the FID score, the likelihood, various different metrics, and they are all indistinguishable. Okay. So it looks like you still get images probably from the same support even for high dimensions. even though this is a low dimensional. Basically it applies, the theory applies beyond when you have absolute continuity. To make another illustration, here is a conditional flow matching. So a different generative model. This is the same target density that I showed you before. This is generated with epsilon equal to 0. So this is a generative model without any errors. And this is with order 1 errors. Okay. So with order 1 errors, you can see the generated density. This does not look like the green picture I first started with from the diffusion model. Okay. So it looks like if you change the algorithm, you may or may not get this robustness of the support. So what is it about the dynamics? So we've introduced all this elaborate notation to represent this generative model as a dynamical system. Can we do some further analysis in the situation where A, the target is not absolutely continuous, it's singular, and B, to explain this observation that some generative models can retain the support under errors whereas others cannot. So to understand this, let us look at again error propagation in the tangent space, which is simply defined like this. Okay. Constructively, let us take E0 to be some little d dimensional subspace. So it is just a matrix with orthonormal columns, right. That is E0, which is little d dimensional, where little d is the dimension of the support of the target. It is strictly less. Okay, if it is equal, then you have an absolutely continuous target. If it's strictly less than the capital D, the ambient dimension, then we have a low dimensional manifold supporting support for the target. Now let's define these ETs just constructively as the dynamics under the Jacobian map of the generative model. Okay. So this is the Jacobian map of the generative model. I'm taking some random orthonormal matrix E0 and then propagating this. Okay. And then to always keep it orthonormal, let us do a QR decomposition. If you have seen something like this before, you would note that as you let t to infinity, there are many asymptotic properties that are known about these ETs. They are related to what are called oscillated spaces. For this forms a part of even for theory of non-autonomous dynamical systems. These are supposed to characterize the different directions of differential sensitivity of perturbations. Okay. You can, if you haven't seen this before, do not worry. Think of these as nonlinear extensions of eigenvectors. So if instead of this Jacobian matrix dft at x changing at x and time, if you just fixed it to be a matrix, then if you do this, this is the QR iteration to compute eigenvectors of a matrix, and eigenvalues will be in this R matrix, right. So you can think of this as a nonlinear version of that. And in finite time, because these models are not defined for infinite time, as we have said, they are only defined from 0 to tau, okay. Because at tau, beyond tau we do not know how to extend these models, we have only learned it for some time 0 to tau. So in finite time, these are indeed related they have been used before in the physics literature and fluid dynamics literature in the form of these Cauchy-Green tensors. Okay. So these ETs are related to the eigenvectors of DFT transpose. Okay. What do they tell you? They tell you what are the most sensitive directions in the tangent space where errors can grow. Okay. So if you take the top D, as is convention even with eigenvalues, we typically arrange them in decreasing order. So these are the top D corresponding subspaces where errors are growing the most. Okay. Maybe all the eigenvalues are negative, in which case it is still where the errors are decaying, but these are the most sensitive subspaces. Okay. And to recover what are called Lyapunov exponents, defined for again for finite time, we will define them as the mean of the log diagonal of these R matrices. So this is a very easy construction to recover the most sensitive directions in the tangent space, as well as the corresponding exponents that tell you how fast errors are growing or decaying on an exponential scale. Okay, this is all well and good. How do these things look, right? Let me help you visualize them. So here is again a score-based diffusion model. Here is some target density, and here is the target density for epsilon not equal to 0. So you can still see that the samples you get are roughly speaking on the same one-dimensional manifold. And here is the more interesting part that I wanted to talk about. These are the visualizations of ET. Okay. So here E is one-dimensional because the manifold is one-dimensional, and we've defined E as the subspace with D columns, D many columns, or D is the dimension of the manifold. So here is the D is 1, and you can see curiously that at all the sample points the line which represents ET is tangent to the manifold. Okay. So you can immediately connect this to several different works that have asked similar questions. Is do diffusion models learn the data manifold? They have taken various different approaches. These in this work that Seating also mentioned, they look at what leads to memorization of the samples and what leads to sampling exactly from the support of the data distribution, empirical distribution. In other works we have seen there are estimates of the dimension of the data manifold given by the generative model and so on. Here we are asking, in the tangent space it looks like there is learning, it is learning the data manifold, and can we formalize this? Okay. Diffusion models are learning the data manifold. How do you formalize this? One way to formalize this is to say that when you have this alignment property, which is defined as if you take this most sensitive subspace ET and it exactly spans the tangent space of the data manifold. M here is the data manifold. For now let us just assume this is some smooth manifold. Okay. So ET, if it is exactly spanning the tangent space, we will say that a generative model is aligned. Again, recall that ET is a property of the dynamics of the generative model, okay, and TXM, this tangent space, is simply is a property only of the target distribution. It does not have anything to do with the generative model, right? But if these things are the same, then we say that the generative model has this alignment property, and we can say that informally we can prove that if you have an aligned generative model, and convergent here means that you have theoretical guarantees for the generative model. That means that if you make 0 error in the score, you recover the distribution. Okay. So recover the distribution, say in Wasserstein distance or TV distance. I will not go into the proof, but it basically learning here, learning the support means that if you use the predicted samples to learn a classifier for the support, you can actually use an aligned generative model. Remember that the aligned generative model is making mistakes. It is not getting the density right, but it is making mistakes in such a way that if you take the predicted samples, you can still learn a classifier for whether you are on the support or off the support with very small generalization error. Okay. So it is as good as having, if your goal is to just learn the support, it is as good as having a correct generative model. Having this incorrect but aligned generative model is as good as having the correct generative model. Okay. So let us see this visually. Okay. So here is some noise sample. Here is the MNIST sample 4 that is generated by a by a generative model that is trained on these MNIST digits. Here is this same 4 plus the most sensitive Lyapunov vector. Okay. So that ease that I showed you, if you take the first column, that is the most sensitive one. So if you add this to this vector, so this vector can also be visualized as the image because recall is the same dimension as the image. You get this, which also very much looks like a 4, right. So it is on the manifold. The last one is this 4 plus the 100th most sensitive Lyapunov vector. 100 is much greater than the intrinsic dimension of the manifold. So we believe that the error made along this 100th most sensitive one is going to take you off the manifold, and that's what you observe, like empirically this 4 doesn't really look like a 4. Right? You can also see this in the Lyapunov exponents, where if you plot the Lyapunov exponents using the procedure that I just described to you from the matrix R, you will see that the first 20 or so, which is close, I think maybe 15 is the dimension of the intrinsic dimension of the MNIST data set. You see that the first few are separated from this whole band of the remaining 760 or whatever, and these are correspond to errors of the manifold, and the most sensitive exponents are corresponding to moving along the manifold. So there are mistakes of the density on the manifold, but you still get digits from this diffusion model. Okay? So this is all well and good, right? We can ask, okay, can we say more? So if you give me an arbitrary generative model that has this just convergence property, that we know that with 0 errors it can recover the actual distribution, can we say what about the dynamics leads to this alignment? Okay, what should the dynamics look like of the generative model? So dynamics on probability space or dynamics on sample space to get this alignment property. And we think that it can happen for a wide class of generative models. Unfortunately, I can only get a sufficient condition, which is basically saying one intuitive understanding that we can get from the sufficient condition is that if you have a dynamics of the generative model which is such that towards the end, as t goes to tau, you have a huge compressive force towards the target samples, which is towards the data manifold. This leads to alignment. Okay. And really this result itself is not that illuminating, but perhaps just this expression for the score can be informative in itself, and that is why I put it there. This is how it is proved. You basically look at the score, these are the scores, so gradient log of the densities along the orbit as time varying with time. Instead of looking at the evolution, and you can derive the evolution of these scores by doing change of variables, taking the log and taking the gradient. Okay, the expression looks hairy, but really it's change of variables after taking log and gradient. And further, it is interesting to project the score onto these ETs. Okay, so this is a projection of this is just the dot product of ST along ET, and if this goes to 0 as time increases, that's when you have alignment. What does this going to 0 mean? It means that the score is orthogonal to the most sensitive subspaces. And remember that if your target distribution is truly low dimensional, the score is orthogonal to the data manifold at the final time. Okay. So if the score is orthogonal to ET and this score is orthogonal to the data manifold, ET is tangent to the data manifold. This is the mechanism for if this thing is controlled, and this is a recursive equation. So arbitrarily you can set S0 E0 to be 0, and so if this angle between the ST and the ET goes to 0, that's when you have alignment. And for diffusion models you can show that this happens. So that's why this explains our picture. So some of the stuff about the dynamics are evident here. These are the directions of the score at the initial time. These are the directions of the score at the final time. You can see that there is a strong contraction towards the manifold. This makes that ST, ET go to 0 actually. And then you get alignment, which is shown here because these are the directions of E which seem to be tangent to the manifold. Here is the last picture I will show you about this. I have 3 different algorithms: optimal transport conditional flow matching, stochastic interpolance. Okay? So 3 different ideas for generative models. On the top picture you see in red the top Lyapunov vector, most sensitive direction, in blue the score. Okay. Of course, you can't see the orthogonality as much here. So, I am showing you a histogram of the angles between the score and the E. Okay. For these 3 different algorithms, it seems like this one is the most aligned because it's almost close to 0. The angle between them, oh sorry, it's the cosine or the dot product, it's not the angle, it's the dot product. So, when it's close to 0, they are orthogonal. This seems to be the most aligned compared to this and this, and we see this reflected in the robustness of the support. So, when you don't have much alignment, which is this case and this case, the support looks very far away from the actual target support, the 2 moons, than this one, which seems to be the best among these conditional flow matching, but the diffusion seems to be better than all of these conditional flow matching. Okay. So, to summarize what I have said so far, what we know is that alignment of the Lyapunov vectors happens, Lyapunov vectors meaning the most sensitive directions in the tangent space where errors propagate. This happens, and when this happens, we get robustness of the support. Many different kind of dynamical systems for the generative model can lead to this alignment property. And really, when you have this alignment property, the generative model acts as a manifold learner in a very precise sense, in that you can actually recover the support of the target distribution just by looking at the samples of the predicted distribution. And lastly, whenever we describe a property, we want to know, does it hold under perturbations? What is the regularity of the property itself? This is saying that if your generative model has the alignment property, perturbations of the generative model retains the alignment property. So, that is all I wanted to say. I will just conclude here and take questions.